Okay, it may look somewhat strange. Those of you who are familiar with calculus or real analysis, they will think of this as the closed bounded interval on the real line. However, for some reason, Herstein chooses to use this to denote the LCM of A and B. More commonly, it's denoted like this, but we are not going to use this. By this, okay. So now prove that this exists and that this is related to the GCD of A and B in this way. If A and B are positive. Okay, now a word about the integers A and B. If you recall, in case of GCD, we came across one situation like this. The greatest common divisor of A and B does not exist if both A and B are equal to 0. We haven't said anything like that here. Why? You see, from the fact that we have these two divisibility conditions, we are forced to consider only non-zero A and B. Both A and B in this case have to be non-zero. Otherwise, these two things don't make sense. If one of them is 0, we can't even talk about something like this. Because for divisibility, the divisor must be by definition non-zero. So in this case, it's given to us, it's implicitly assumed that A and B are non-zero. So with that, we now start the solution. Okay. So let us see how we can solve this. The starting of the solution is somewhat similar to the one the result that we proved for GCD, namely that GCD exists for two integers, at least one of which is non-zero. So in the starting of that proof, we considered a set. Here also we are going to do something similar. Consider the set D equal to, it's the set of all integers. Okay, by J, Herstein means the set of all integers. The other notation is this blackboard bold Z. So D is the set of all integers that are positive and that are divisible by both A and B. So in other words, D is the set of all positive integer multiples of A and B, common multiples of A and B. Okay. Now, D is non-empty since, okay, why is it non-empty? It's because this integer, which is positive, you see, the fact that both A and B are non-zero, which we are not even mentioning simply because they are contained in these relations. These two conditions ensure that AB is not equal to 0, and from the definition of absolute value, we already know that absolute value of any integer is non-negative. Now, because the integer is non-zero, it can't be 0 also, so it is strictly positive. Since this belongs to D, Okay, this is strictly positive, but why does it belong to D? It belongs to D because it's a multiple of both A and B. That's why. Hence, okay. So now we have a set of positive integers which is non-empty. So we can use the well ordering principle here. Hence, by the well ordering principle, D has a smallest element, D, say. We are denoting it by D. Okay. Now our claim is that D itself is the LCM of A and B. We claim to show this, we need to show these two things. Okay. Since D belongs to D, we have, just from the fact that D is the smallest element of D, since it is in D, it is divisible by both A and B. So the first condition is it comes just like that. Next, let C be a positive integer. Oh, positivity is not mentioned here. We don't need positivity. Let C be such that C is any integer which is divisible by both A and B. Okay. Now by the Euclidean algorithm, there exist integers. We have used Q and R so many times, no? There exist integers, say M and N. We can use M and N. In the context of this exercise, we can use them, or we can use Q and R themselves. It does not matter. There exist Q and R. The thing is that we should not lose track of the variables that or the numbers that we are using. If these names have already been used somewhere in the solution itself, then there will be a problem. Since we haven't used Q and R anywhere in this solution so far, so we can use them here, such that, okay, so what are we doing here? Here we are trying to divide C by D. Note that we can speak of division of C by D because D by definition is non-zero. In the set capital D, no integer is zero. All of them are positive. So D, small d being an element in capital D, it's also a positive integer. So in particular, it's non-zero. So such that C is equal to QD plus R, and where R satisfies these inequalities. Okay. Now, since D divides no, not D, A. Since A divides C, A divides or B divides C, A divides D and B divides D, we have these two relations are coming from the fact that D belongs to D or here, and these two are things we have assumed. So because of this we have A divides C minus QD, which is R, and B also divides C minus QD. So R now is an integer which is divisible by both A and B. So you can put R here, but you see this R is less than, oh, it should be D, sorry, D, because we are dividing by D. Okay, sorry about that. R is less than D and D is the smallest element in capital D. So R cannot be positive because otherwise the smallest nature of D, the status of D as the smallest positive common divisor of capital D is violated. Hence, R less than D forces us to conclude that R must be equal to 0. There is no there is no possibility for R to be positive due to the minimal nature of D. Hence, now because R is equal to 0, so D divides C. And this was precisely the second condition for D to be the least common multiple of A and B. Thus, D is this. Okay, so this completes the first part of the solution. Now we come to the second part. Now we assume A and B to be positive integers. Okay, now if that is the case, then we have to show that the least common multiple is equal to AB divided by the greatest common divisor. This, we have to show this relation. Right. So we start like this. Since the greatest common divisor by definition divides both A and B, it divides B also, we have how? What have I concluded here? You see, because the greatest common divisor is dividing both A and B, this number, this integer, is a multiple of both A and B. Why? Because I can write this integer. It's an integer, first of all. Keep that in mind. I can write this integer as A times B divided by the GCD of A comma B. Now, let me not use the square bracket. Now, this is an integer. this is in J. Why? Because a comma b is dividing b. So b divided by a comma b is an integer. So this turns out to be an integer multiple of a. Okay. In other words, this number is divisible by a. Similarly, I can also write it this like this. Since the GCD of a and b divides a as well, this is an integer. So this turns out to be an integer multiple of b, and hence I also have this relation. Let me write it here. B is dividing this. Now this is an integer divisible by both a and b. So by the second condition from the definition of an LCM, the LCM should divide this common multiple. This is the least common multiple, this is the common multiple. That's why we are getting that's how we are getting this relation. Okay. Now, but we already know that the GCD of a and b is an integer linear combination of a and b. So we can write it like this. This is equal to MA plus NB for some integers m and n. This implies, now multiply both sides by the LCM. What shall we get? LCM times GCD is equal to MA times LCM plus NB times LCM. But we also have now by definition, this number, the LCM of a and b, is a common multiple of a and b. So it should be a multiple of a. Let me write alpha a, and at the same time it should be a multiple of b, that is beta b, for some integers alpha and beta. Okay, this is coming from the first condition, that a and b are both dividing this number. So it should be a multiple of both a and b, integer multiples. Okay. Hence, now use these expressions here, but cleverly. LCM times GCD, so that we get something. Okay, now MA, in place of this LCM, we will write beta B. This is equal to beta B plus NB. In place of this LCM, same thing, but we are going to write alpha A, because after all they are same. So what does this give me? I can take A, B common out because they are available in both the terms. So I get N beta plus N alpha times AB. Okay. Now you look at this. Remember, we continue to have the fact that A and B are both non-zero. Otherwise, this does not exist or it's meaningless. So that's why AB is non-zero. So now we have realized this product as AB times something. Now this something is an integer. Why? Because alpha, beta, m, n, all of these are integers. So this is an integer. So that means AB divides this product. Hence, AB divides this product, but that's not what I want. Wait. Or I can rearrange this slightly differently. Let me continue. Or LCM is equal to m beta plus n alpha times AB divided by a comma. This is what I wanted to write. Now we already know that this AB divided by GCD, this is an integer, and looking at this equation, I can now conclude this. Therefore, this divides the LCM. Now we look at these two relations. This one and this one. So it's that same situation where I have already used CNB. No? Suppose say gamma and delta are two integers. Gamma is dividing delta and also delta is dividing gamma. Then we have already seen, I think this was the first or second exercise, that gamma is equal to plus or minus delta. So here also the LCM will be equal to plus or minus AB divided by GCD. But A and B are both positive, right? See, that was the additional assumption. A and B are already non-zero, but one or both of them may be negative. But now additionally A and B are positive. So this is a positive integer. GCD by definition is positive, but now A and B are positive, so this is a positive integer. And that's why this is also a positive integer by definition. So there cannot be any minus sign. So from this dividing AB by A comma B and this also dividing the LCM and positivity of both these numbers we get what we were trying to prove. Okay, so here the solution ends. Next we have exercise 4. What this one says, if A divides X, X is some integer, A and B are also integers, and B divides X, and there is one more condition, A and B are relatively prime, then the product AB also divides X. Now for this one, the solution, it uses the previous result or the result of the previous exercise. Since because yeah, I have to mention that thing. Okay. Now these relations, these divisibility relations already contain in them the fact that A and B are non-zero, but they may be negative also. However, since sign does not affect divisibility, you see, 2 divides 4 in much the same way minus 2 also divides 4. So when you have divisibility, whether you include a plus sign or minus sign, that does not matter. So we are going to write something like this. Since sign does not affect divisibility, we assume without loss of generality that both A and B are positive. Okay, we can assume this. Then by the previous exercise, we have this. Always keep in mind that to be able to use this formula, we have to have the condition that A and B are both positive. Otherwise, this will not be true. Okay, so we have this. However, it is given that A and B are relatively prime, so this is equal to AB divided by 1, which is AB. Okay. Hence, from A dividing X and B dividing X, we have the LCM dividing X. See, this is by definition of LCM. If we have a common multiple of A and B, then that is divisible by the LCM also. But now in our case, the LCM turns out to be equal to AB. So AB divides X, and here the solution ends. Then we look at exercise 5. If A is an integer whose prime factorization is like this: p1 to the power alpha 1, p2 to the power alpha 2, etc., pk to the power alpha k, and b is an integer whose prime factorization looks like this. Same primes but different exponents. p2 to the the power beta 2 pk to the power beta k, where the pi's are distinct primes and these are, I think, non-negative or positive, and each alpha I is non-negative and beta I is also non-negative. So if these things are true, then there are two subdivisions. This is equal to P1 to the power delta 1, P2 to the power delta 2, etc. up to Pk to the power delta k, where delta I is the minimum of alpha I and beta I for all I, and like that there is one for the LCM. The LCM likewise is equal to P1 to the power gamma 1 times P2 to the power gamma 2 up to Pk to the power gamma k, where gamma I in this case it's maximum of alpha I and beta I for each I. Okay, now we come to the solution. So we have to show that this number is the GCD of A and B. Okay, one thing you can notice here is that we haven't said anything about whether A and B are at least one of them is 0 or not, but you can see that those things have been taken care of by the fact that this number or this integer has a prime factorization. So for 0 we don't usually write factorizations like this. I mean, we cannot have, you see, because all the factors are powers of primes, and no prime power can be 0. So that's why from the way this has been written, that itself tells me that not only is this not 0, but it is positive also. Because you see, according to our definition, the prime numbers that we are considering, we have already defined prime numbers. Some of them are negative also, but we have said there itself that we are not going to consider negative prime numbers. For us, primes are positive. So in the extreme case, when all the alpha i's are equal to 0, A becomes equal to 1. So that is the least value A can have. Otherwise, it is greater than 1. In other words, both A and B are positive integers. Okay, that becomes clear simply from these expressions. Now we start solving this. Okay, so just like that, since A and B are positive integers and the way they are given, so this number is also a positive integer. Okay, so it makes sense to wonder whether these two are equal, because by definition the GCD is a positive integer and this is also a positive integer. We have to now show that these two are equal. And to show that, we will use the definition of GCD. What is the definition? The definition says that this is a number, this is a positive integer that should be, or I should point towards this. This is a positive integer that should divide both a and b and should be divisible by any integer that also divides both a and b. Okay, so first of all, we have to show that this divides both a and b. Since delta I is the minimum of alpha I and beta I, we have pi to the power delta I. It divides pi to the power alpha I and pi to the power delta I also divides pi to the power beta I for all I. Why? It's because since delta I is the minimum of alpha